Ooh, for you. I just want to know which flavor it is. The orange one's not one of mine. Sucker? Yeah.
Okay. How are you all doing? Happy Monday. Ooh. Do you have midterms starting to pile up?
Yes,
Just I feel like the evil queen.
And this you still feel like the queen.
Oh yeah. Okay, so it's next Monday, you guys, your midterm. And as always, I recommend that you study, then you solve the midterm example from last year before you look at the key. The other thing I want to remind you, don't get overwhelmed by the key because as you see now, we're going to give you back your quizzes. We don't go word by word if you didn't get the key. My keys are usually detailed because it's education. I'm still trying to teach you. Okay, as long as you get the idea. Okay, and if you have questions between now and next week, let me know. And everything will be on the midterm up to Friday's lecture. You can get started studying, and then in the weekend you study the last lecture, and hopefully you can review and solve the quiz, the exam, and be ready. It'll be very similar to last year exam, obviously different questions, but yeah. Okay, let's continue. I know I'm in the middle of your MS lecture. It's just because I had to be at a conference last week and I'm at conference this Wednesday. So I put Gary where I'm not going to be. So that's why I'm going to be doing this lecture and Gary's going to come back on Wednesday to finish his MS. Okay. All right, so let's continue with spectroscopy. I know I did AA before this lecture, although AA is under the umbrella of 3D visible spectroscopy. But let's talk about principles of UV vis. Have you heard before about the term molar extinction? Does it ring a bell? Molar absorptivity, does it ring a bell? Yeah, sort of. We're going to talk about it today. So molar extinction coefficient is a constant for all analytes? No, it's not. Every analyte has its own absorptivity. Molar extinction has to do with absorptivity or the unique characteristic of a particular analyte to absorb light. So it's a very specific constant based on the structure and configuration of that analyte. A high concentrated sample may result in deviation from Beer's law. We're going to talk about Beer's law. And last time we kind of mentioned it briefly that it is the linear relationship between absorption and concentration. And if we have very high concentration, we get molecules to interfere with each other and affect their absorption. So we don't want to have high concentration when we're measuring absorption. So B is correct. And then incident beam minus exiting beam is equal to the light absorbed by the analyte. What is incident beam? So you have your sample in a cuvette, or the sample is going through your flow cell in a detector, HPLC detector. So the light is hitting a sample, that's incident beam. And the sample is going to absorb light, and then we have the exiting beam, because not all light is going to be absorbed. So what this is saying is the incident beam minus the exit beam or transmitted light equal the absorption. Do you think is correct? It seems logical, but it's not correct. And I will go over why it's not correct in the slide. So The only correct answer here is B. Okay, so mark that as a correct answer, and then we will discuss all the points during the lecture. Okay, in absorption and fluorescence spectroscopy, UV vis radiation is used. The transmitted beam is the signal measured. So after the incident beam hits the sample, what comes out, the transmitted, is what is measured. A grating monochromator is needed. So what's your best guess? This is what applies when you're in doubt. So yes, so if you remember, or when you study, try to remember that absorption and fluorescence happens in the UV visible radiation spectrum. So when you measure absorption and when you measure fluorescence, you're often in that range, in the UV vis radiation range spectrum. The transmitted beam is actually what's get measured by the detector, and then absorption or fluorescence is determined, okay? A grating monochromator is needed, yes, when we're doing quantification. If we're just doing structural identification and qualitative analysis, not necessarily. But if we are doing quantification using Beer's law, we need to do that at one wavelength. So we need to diffract the light into multiple wavelengths, and we need to select that one wavelength for us to do the measurements of absorption and determination of concentration. Okay. So we use UV visible spectroscopy to measure absorption or fluorescence for both qualitative analysis and quantitative analysis. Qualitative is for detection and identification, structural elucidation, but quantitation is when you want to determine the concentration of the unknown. So sometimes the analyte is a chromophore, meaning it naturally absorbs light. Sometimes it naturally fluoresces. So it's an inherent signal. But there are components that don't absorb light. For example, can you think of a component in food that does not absorb light naturally? Yes, thank you. Carbohydrates, sugar, they're not very special like proteins. they, they don't absorb light. Don't tell George I said that. So they don't absorb light, but we can chemically induce light absorption by reacting them with a reagent that forms another compound, and that compound will absorb light. And usually if it's a stoichiometric reaction, then we can determine the concentration of that analyte that didn't originally absorb light. And sometimes, even if it's not a stoichiometric reaction, we can still measure concentration. I just remembered that there is a process we're going to have in the lab, total carbohydrate analysis, which is not a stoichiometric reaction, but we're converting a glucose into a compound that absorb light or sugars. Okay. So we can use that for quantification of macro components like the total carbohydrate biphenyl sulfuric acid assay. We're going to do that in the lab in a couple of weeks. We can use this UV vis spectroscopy to determine microcomponents. For example, vitamin, thiamine, we measure fluorescence. So we use this thiamine fluoresces so we can measure the fluorescence and determine concentration. Absorption is also used in ELISA, enzyme-linked immunosorbent or immunosorbent assays, yes. So in that, we can determine the presence of an antigen either by reacting it with a component that gives light or that antigen itself absorb light. So these are just examples, but in the future we're going to talk about different components, and we're going to use spectroscopy almost in many, many cases, if not all the time. All right, so now let's talk about this Beer's law and incident beam, exit beam, which we can also call transmitted light, and then absorbed light, and all of these different combinations. So when we are determining absorption, it's really determining the amount of light or energy absorbed by a reference beam as it passes through the sample. So this is the easiest way to comprehend it, is to have your cuvette that goes into a spectrophotometer. So the B stands for the length. So that means the distance the light passes through. And then C for concentration, A for absorptivity, which is very, very specific to the analyte. And PO stands for the incident beam, or the light that hits your sample. And then P is the exit beam, or the transmitted beam, or the light that reaches the detector. So you have the light goes in, stuff happens other than absorption. I'll show you, not just absorption. And then less energy, transmitted light, goes to the detector, gets analyzed, and mathematical calculations happen, and an absorption is determined. So the transmittance of a solution is basically the ratio of the exit light to the incident light, and percent is you multiply that by 100. So it doesn't have a linear relationship with concentration. And in food analysis, we like linear relationship. It's much easier to work with. To determine concentration, we like linear relationship. So absorbance, on the other hand, has a linear relationship to the concentration, and Beer's law defines this relationship. The relationship of absorbance to concentration is defined by Beer's law. So absorption in relation to the light is the inverse of log the inverse of transmission. So log P0 over P, or minus log T. Okay, so the detector does all these calculations for us. You don't have to worry about it, but you really need to know that absorbance is the negative log of transmission, and it has a linear relationship to concentration, and this is Beer's law, or Beer's-Lambert law. So it's two people that came up with this law, and sometimes Lambert is dropped for some reason, and it's only known as Beer's law. So this is A for absorption, the capital A. The small a, or the lowercase a, is absorptivity, which is unique, a constant unique to the analyte. B is the distance of that the light travels within the sample. And C is the concentration that we're trying to determine. That's the, and then since it's a constant, there's no specific unit for absorptivity other than the inverse of centimeter and concentration. So because absorption doesn't have unit, so the absorption is absorption units, it's called like that. And then B is in centimeter. Concentration is either in a percentage, milligrams per ml, or molarity, or whatever it is. And then A would be the inverse of centimeter and the unit of concentration. Therefore, absorption doesn't have an actual unit. So that is what this is saying. And this epsilon here is referred to, A is referred to epsilon when the concentration is in molarity. Then it is molar absorptivity or molar extinction. So that's the first question that you had beginning of the lecture. What's molar absorptivity? What's molar extinction? Is this letter, small letter A, known as absorptivity? It's referred to as molar absorptivity when the concentration is in molarity. Otherwise, it's just called absorptivity. Okay. So what is this absorptivity dependent on? You think? All of the above. When I'm quiet, the answer is easy. It's all of the above. Now, so it is, like I said, it's very specific for the molecular properties of the species. Its structure, its light absorbing components, functional groups. It's very unique. It changes with the wavelength because you have different absorptivity at different wavelengths. That's why when we are measuring concentration, we have to select one wavelength. And also, it's advisable that we select lambda max for maximum sensitivity. Chemical environment is very important because especially if you have analytes that would have groups that dissociate, like acid-base, or things that will have a functional group that can dissociate in solution. Okay, so when compound, let's say, easy to think about, loses a proton or gains a proton, their ability to absorb light changes because now we change their molecular properties. So it's very important that the chemical environment is constant. That's why sometimes we have to have a pH or buffered, pH controlled or buffered environment so that we have a constant absorptivity. So all of that. All right, now here's going to explain why incident beam minus transmitted light is not absorption. It's not equal to absorption. Because you have light that gets reflected. So light hits this surface of a cuvette. Some of the light, like a mirror, gets reflected back. Some light gets scattered because you have molecules that could just scatter light and go in different directions. Some light gets absorbed. So that's why the absorbed light is not equal incident beam minus exiting beam, because there are other losses of light. And that's why it's very important to have a blend. When you're measuring absorption in a spectrophotometer, you learn that in lab in a couple of weeks, you will have a reagent blend. So you will have a cuvette with a reagent blend, and then you will zero the spectrophotometer so that to account for differences that are not necessarily just related to the absorption of the analyte. So that's why we use a blank, or sometimes some spectrophotometer has two places for cuvettes, one for the sample and one for the reference or the blank. And simultaneously, you get absorption of the blank and the sample, and you get a corrected absorbance. So deviation from Beer's law, it's important to know when you're setting up your assay, spectroscopic assay. So we do not want to work with a really high concentration. So it's always a dilution step. And you'll see that in some of the labs already diluted caffeine, for example. Later on, we're going to be diluting the carbohydrates in a sample so that we are, first of all, in the range of the linear range of absorption to concentration. And also, it's not very high where compounds are going to bump into each other in solution. And then because you have very small distances between the molecules in solution, and then they will interfere with each other and change the absorptivity characteristic. And then if we don't have a constant absorptivity, Beer's law cannot be followed. Also, if we have components that get ionized by shifts in pH during a chemical reaction, or they have dissociable functional groups, then we need to make sure we control that by a specific pH or salt concentration. And then we talked about making sure we don't have a polychromatic light, meaning you don't have light of multiple wavelengths. Beer's law cannot be applied because absorptivity is dependent on the wavelength, and concentration is linear only when we have monochromatic light. That's when we want to measure concentration. We want to make sure the light is monochromatic. Okay. So another thing with measuring absorption is you don't want a turbid sample. So if you prepare your sample and you look at it and you see it's not clear, it doesn't matter if it's colored. Colored is fine because you're probably measuring absorption at a particular color wavelength. It has to be clear. It cannot be clouded. If it's clouded, then you will get false absorption because a lot of light is going to be scattered. So we don't want a sample to be turbid. We don't want particulate in the solution. So it has to be homogeneous. It has to be clear. Sometimes we have a centrifugation step that we do to clarify that solution. And we need to have a reference or a blank so that we can take into account other reagents that might absorb in the same wavelength that we are measuring the analyte. So we need to correct for the absorption interference by the reagents used. So these are important considerations, always making sure we have the correct blank. So the blank usually have all of your reagents except the analyte. And making sure that the solution is clear and homogeneous. Then we have the different cuvettes that we can use. So quartz is the most expensive and durable and mostly used for UV. Fused silica can also be used for UV. If we know that we're measuring invisible range, we can use glass or plastic. They don't absorb in or interfere with light at the visible range, but glass and plastic absorb UV light. So they will interfere. We cannot use them for UV. And also the size of the cuvette, sometimes we're limited by our sample volume. So if our sample volume is limited, we can use cuvettes so that are narrow inside so that we reach a certain height because the light needs to go through the sample. If you don't have enough sample, the light will go above the actual sample and then you won't get measurements. So that's why we want to make sure that the height is above the light passing through. Okay. So selection of the wavelength, we need to select the wavelength where we have the highest absorption and also when it's steep, meaning we want to select an area where the difference in wavelength is very, very narrow, so it's sharp. So if we have an area like this, like shoulder, so 352 is very close to 353, for example, and very close to 360 potentially. Then we have multiple wavelengths that is passing through this monochromator. We will not be following Beer's law. So we have to be in an area that is really steep so that the bandwidth is very steep. Only the selected wavelength will pass through and we have the maximum sensitivity. We always calibrate the instrument. This is different from zeroing. The way we calibrate it is we block the light path and we say this is zero transmittance. We tell the instrument this is zero transmittance. And then we don't have anything in the place of the cuvette holder and we unblock the light and we say this is 100% transmit. So that's calibration that's separate from zeroing. Okay, so here when I mentioned it briefly during the AA lecture, where we want to make sure that we prepare our standards in the linear range of the relationship between absorption and concentration. Some of you did the AA last week lab. You did calibration curve for calcium. You did calibration curve for iron. The linearity range for iron is much smaller in concentration than the calcium. So you will notice that if you haven't done the lab. So even at the same concentration, one compound has linear relationship, another compound doesn't. So we have to reduce the concentration even lower so that we can get into the linearity of the relationship between absorption and analyte. So we need to figure out this linearity. That's why we have to do trials. First, determine what's the concentration of the standards I need. So when I plot absorbance versus concentration, I have a linear curve. So oftentimes, the method that you are using has already been solved for you. You already have standard operating procedure. But if you're doing completely new method, you really have to empirically determine that. So you really need to prepare different concentration and plot the absorbance and see where that linear range is. Once you identify this linear range, then you have to dilute your samples so that the concentration is within that linear range. That's why when you do the lab, the atomic absorption lab, you'll notice that the dilution for calcium is different than the dilution for iron. And you have to make sure that your dilution is within the standard curve. Otherwise, you overestimate or underestimate because you're not in that linear range. Cannot apply the equation because you're not in that linear range. All right. Questions about that? All right. Now I'm going to explain a little bit of a complex concept. So I said we need to have blanks, and the blanks have are made up of the same reagents without the analytes. So that reagents are not interfering with the absorption, you correct for that. That's easy. But sometimes your sample itself has interfering components. The matrix of your sample itself has interfering components. So it's really hard to do a standard curve and a blank and avoid the inherent interference within your sample. So there is a way to solve that. And this is by using standard addition protocol. Okay. So I'm going to draw so that you visually see that. So your standard curve or your standards that you prepare actually have your sample in them. Instead of preparing your standards separate from your samples, you prepare your standards and you have your sample in each of the standards. This is different than internal standard that you learned last time. Internal standard is you put internal standard in all the samples and all of the external standard. That's not the same thing. So what this is you get your, whatever it is, 10 milliliter volumetric flask. Let's say you want to prepare a standard curve with 5 different concentrations. So you get your volumetric flask, 10 milliliter, excuse my drawing, I'm navigating that in drawing. Can't draw the same volume. So let's say you have 5 10 milliliter volumetric flasks. So what you do is you add to each one of them a known, well, the same volume of the unknown sample. Let's say 10 ml, 10, or let's say 100 microliters. So you add that to all of them. Okay. So now you have the same volume of your unknown sample in all of them. Now, what you do is you add to each one of them a volume of your standard, a stock solution. So let's say here you have a stock solution of your standard. You add here, let's say you added 2 ml. Just an example. And then here you add 4 ml. And then here you add 6 ml. 8 ml. I'm just giving an example, okay? And then or 10 ml. So what you're doing is you're adding a different concentration of your standard in all of these different flasks. So now you have 5 different concentrations, 1 stock solution from standard, 5 different volumes. So you're building your standard curve with the same volume of your unknown. Same volume goes into everything. After you add your standards, you make up the volume, your 10 ml or whatever is your volume. And now you have built a standard curve with your sample. You measure absorption over concentration, but now the equation of the line has all of these different components: volume of the standard, the concentration of the standard, which you know already, volume of the unknown, you know, because you put the same volume in all of them. Then you solve for the concentration. You know the total volume, let's say 10 ml in this case. You have the constant absorptivity. Then you measure absorption, and then you determine concentration of the ion. That's called standard addition protocol, and it's used for complex matrices of a sample that might have interfering components that can absorb at the same wavelength. So that's the only way you can get accurate determination, is building a standard with in a complex matrix. Questions about that? You're taking the picture. Did you take me in the picture? No. Yeah. Okay. You heard of the term noise? You know, instrument noise. So that's when you have noise, we call it error, that you have to account for. And you probably seen that, those of you that did MS, you saw those little spectra that you said, okay, I'm not gonna measure those. This is instrument noise. So you always want to have an absorption of an analyte larger than the noise. So you want the noise to be indiscriminate, very, very small compared to the actual measurement and absorption. Every instrument has instrument noise. And sometimes you'll see that when you do the total carbohydrate lab, we don't have a spectrophotometer with the reference and the sample cuvette. We only have one placement. So you put the blank, and then you zero the instrument, and then you put your sample and you measure absorption. You have to, every now and then, take the sample out, put the blank again, and zero, because there will be deviation over time. So that's because of instrument error, noise. So the instrument noise, we need to calibrate, we need to have a blank, we need to ensure that this noise is as small as possible relative to the absorption. That's why we don't want to prepare a very diluted sample. You know, you don't want absorbance to be 0.02. It's very, very small and could be very, very close to the noise. So you want an absorption, usually rule of thumb, they tell you you need an absorption between 0.2 to 0.8 absorption unit. This is kind of rule of thumb. If it is really low absorption, 0.02, that's very close to potentially noise. And if it is 1.2 or 2 or whatever, then this is too concentrated. You might have deviation from Beer's law. But anyway, here we're talking about this instrument noise has to be small, can be tested to know the noise. You can test it to see how do you test it. So you're measuring the same sample multiple times, and the absorption is reading 0.659. Take it out, and then you measure again. It's reading 0.658. And then you read again, it's reading 660. So your noise is 0.001. So you determine your noise because that's every time you measure the absorption, there's a slight difference. It's not always the same. And then once you know what your noise is, you adjust your concentration so your absorbance are way larger than that noise. Okay, so basically the answer to this is all of them. All right, we've talked about monochromator many, many times, but this is the visual of it. So in a spectrophotometer, it's easy always to visualize a tube or a cuvette where your sample is in. So you put your tube, the light is, you have a lamp, you have your tube, you have the detector. So what happens is the light goes, and before it hits the sample, there is the monochromator. That unit has mirrors and grating system and a filter. So basically the mirror reflects the light onto a grating system, and the grating system diffracts the light. So this is the light. Sorry, that's the mirror. That's the entering light. It goes into the diffracting grating system. It gets diffracted into another mirror that gets reflected to where the exit slit is, and then you control that filter that gives you the light. So you can dial it so that you get a specific wavelength going out of the exit slit, which is here, and then it goes onto the sample. That's when you really want a monochromatic light that hits the sample to follow Beer's law. And then it goes to a detector. So the simplest detectors are either a phototube detector, which you have a cathode, the light hits the cathode, an electron jumps off to anode, the electrical signal gets converted into a readout in your device. So you get an absorption. Or you can have a photomultiplier detector like the one with the AA unit. So it amplifies, photomultiplier. It multiplies and amplifies the signal to increase the sensitivity. So the light hits the cathode, an electron, it jumps off, goes to a series of diodes, and multiply the electrons, you amplify the system or the signal, and then you get better sensitivity and lower threshold. Then there is the photodiode array detector that you had in Kefi lab. And in this case, you don't have a monochromator. So this is perfect for structure elucidation and identification. So what happens is you have your light source, all the light gets to the sample, not one light or one wavelength, all the light. So the components within the sample absorb light at different wavelengths. And then the transmitted light goes into a series of photodiodes. What are these? So they're individual photodiodes that converts an electrical signal into a light measurement. And then we get a readout, an absorbance over a series of wavelengths. So all of these lights, we can determine the absorbance at each wavelength. And that's the photodiode array detector spectra that you saw for the caffeine lab. So we see all of that. And then if we want to quantitate, we just look at the absorption at lambda max. And we use that in plotting our standard curve. So we got two things out of photodiode array detector. We get a fingerprint spectrum or spectrum. And then we select one wavelength where we have lambda max, which is the highest absorption at this lambda. And we use that to plot absorbance over concentration and follow Beer's law. So we can do two things with photodiode array detector. Powerful detectors, good to have for structural elucidation. Okay, so now you're experts with monochromators and photodiodes. Any questions? I can repeat. All right. Yes, yes.
One versus the other, because I get how they're different, but like, what's the benefit to using each of them?
What's the benefit of using
Like
a
a
photomultiplier tube versus if you have a photodiode, why would you use a photomultiplier tube or a regular detector? Just let's think together. If you have two in your lab, huh? Which good answer. If you have two in your lab, or if you're a new professor and you were given $5 to start your lab, what would you do? If you don't have enough money, you go with the cheapest option, and the cheapest option is the one that just reads at one wavelength. If you have money and the capability, always good to have more than less. So you get the photodiode, you can do both, you can do structural elucidation, and you can quantitate. So it's always good to have, but sometimes it's limitation of the instrument you have or the budget that you have. If you have MS, even better. You know, it just goes up with what you, NMR, even better. So there's always something better in terms of analytical and power of whether sensitivity, power of detection, power of identification. Yeah. So if you have an option and you have the money, go with photodiode. All right, so the instrument design, I'm not going to spend a lot of time on it with the physics of the instrument. I just want to say that there are two types of instruments, spectrophotometers, single beam and a double beam. The single beam is, you will see it in the lab because that's what we have in teaching lab, is that you would have only one place for a cuvette. So you put the blank, you zero, you take the blank out, you put your sample. And you measure absorption, and then every now and then you have to remove the sample, put the blank again, to adjust for deviation. Now, the double beam is when you have two cells in the spectrophotometer, one for your reference and one for your sample. And then when you don't have to zero, you always measuring absorption of the reference, which is the blank, and the sample, and then automatically get a corrected absorbance. You don't have to adjust for deviation. You always have your blank in there, and then you just take out one sample, put another, and do the measurements. The only thing with double beam is that your source of light is split into two. So you have a splitting. Part of the light goes into the sample, and part of the light goes into the reference. So you have reduced radiant power. So you will have less sensitivity. That's the only thing. But other than that, it's much more convenient to run simultaneously your blank and your sample and get a corrected readout. So you get always the reading, the absorption of the blank, the absorption of the sample, and then it gets corrected right away, and you get your absorption without having to subtract the blank yourself. So I was talking about absorptivity under specified conditions and wavelength. Different compounds, you have known lambda max for them and known absorptivity. So which is, in this case, epsilon, molar extinction. So different compounds that absorb light, they will have wavelength and absorptivity, and therefore you can measure concentration sometimes without having a standard curve. If you know what you are measuring and you know the absorptivity, then you know the distance, then you apply absorption equal A, B, C. The last thing that I want to go talk about, which is perfect timing, is in a fluorescence spectrophotometer, the geometry within that. Remember, the fluorescence is light is absorbed. The compound goes from ground state to excited state. Does it stay there? No. So some compounds emit energy that is measurable, and that is the fluorescence. When they go from excited to ground, they emit light and also heat. Some of the compounds that light emitted, we can measure, and it is fluorescence. Now, how does it work in an instrument? So you have the radiation source. You go into that wavelength isolator is monochromator. Okay. So it goes into a monochromator. You get your singular wavelength light, incident light. It goes to either the sample or the reference or both. Then we have mirrors that will direct the emitted light down here. So fluorescence. So the emitted light, and then this is the transmitted light, the exit light. We don't want that. We want the fluorescence. So it directs to a 90-degree the fluorescence light, but sometimes the compound fluoresces at multiple wavelengths. So you want to select the highest sensitivity, meaning the wavelength where you have the highest fluorescence. So you isolate it again by another monochromator, and then it goes into the detector and then the readout. So you have to remember that you have to set two wavelengths. The wavelength of absorption and then the wavelength of fluorescence. The wavelength of fluorescence is always longer. Why is that? Remember why the emitted or fluorescence light has a larger or longer wavelength than the absorbed light. Why? You remember?
Because some energy is converted to heat.
Yes, because the emitted energy is always less than the absorbed energy, because as we go down to ground state, part of the energy is released as heat. So we always carry less energy in the light that is emitted. And then if you remember the oscillation, you will get that. You would always remember that fluorescence is longer. Because if you have, remember the oscillations? So from here to here is lambda. Sorry, that's my sensor. Then you have like that, you have shorter wavelength. You have more oscillation in 1 unit time. This is higher frequency, meaning higher energy. Okay. That's why shorter wavelength means more higher frequency, higher energy. And longer is lower frequency, lower energy. So the fluorescence light will have larger lambda or longer lambda than the absolute light. Okay, that's it. Any questions? Oh, you have the quizzes. Do you want your quizzes?
So I shouldn't say that. I just think it's not. Yeah, but this is not right.
So I'm just gonna put some metrics for the quiz, the stats.
You're right.
But it's online. You can see it on campus. Campus is down for some reason. Have you guys noticed?
It's been down for a long time,
For a long time?
like a long,
The whole day.
yeah.
Been down since midnight. Yes.
Oh.
Did we get an extension?
That's a bummer. I was gonna say, because someone asked me about remember that question about sampling, the extra credit? I actually put the key on Canvas under week 4. So if you guys want to look at that, it's there on Canvas. Okay.